G'day YouTube. So welcome to the first video on mathematics essentials. So in this video I'm going to cover set notation. So this is part of a section on revision and background knowledge, right? So a set is an unordered collection of elements, right? And I just want to emphasize the fact that it's unordered, okay? The order in which the elements appear in a set doesn't matter. Okay, so we use curly brackets to represent a set, so these kind of brackets, and then we put some elements in the set, and who knows how many it has n many elements, and then we close the set with another brace, okay, or set bracket. Alright, so the order in which the elements are listed is irrelevant, and elements are only listed once, okay? So just to give some idea of why the order doesn't matter in a set, okay, so there are contexts in mathematics in which the order matters, and there are contexts in which it doesn't matter at all. So let's motivate this by some real life contexts. Suppose you are hosting a dinner party, right? And you want to invite everyone by sending out an email. So you're going to send a single email, and you are going to put all of the email addresses of the friends that you want to invite in the address window, so that when you send this one email, all the people that you want to invite get an invitation. Okay, so let's say the people you want to invite, their email addresses are A, B, C, and D. So you're going to invite 4 people to your dinner party. Okay, so it's a set that contains 4 email addresses. Now, if we're just interested in who we are going to invite and who we are not going to invite, okay, well, it wouldn't matter if you entered their email addresses in the population field in the order that I've written it, or in some other order, okay? So, if you just want to, know who you are inviting, or you're just interested in the question of who's going to receive an invitation, then saying Peter, Jane, Sarah, and John, who I am going to invite, is just the same as saying, John, Sarah, Peter, and Jane. Okay, so both of these sets capture all of the information in terms of who is getting an invitation. Okay, all right, so another way to think of it is suppose you're going on a holiday and you need to pack some clothes, and amongst the clothes that you pack, you include a white shirt, a blue shirt, and a pinstriped shirt. Okay, so you can think of, this is a suitcase, a blue shirt, a white shirt, and a pinstripe shirt. Okay, and if you are just interested in what colors of shirts you're able to wear when you are away on holiday, well, this set here captures that information just as good as the other set. Okay, so neither set gives you any more information. Okay, and now notice the part here where we say that elements are only listed once, right? Okay, so this bit here. Let's motivate that. Well, suppose, for instance, when you were sending off the emails to invite someone to your dinner party, you included some email address twice. Okay, so the second friend's email address is B, and suppose you put their email address in a second time. Okay, does the fact that we put their email address in twice change who's getting an invitation? No, the same people are still getting invited to your dinner party, all right? So this is really just equal to this set over here, okay? And also equal to this set, just like these two sets are equal, these ones here, okay? Okay, so if we want to name a set, usually we use an uppercase letter, but not always, okay? So here's an example. So the set A is equal to the set that contains 1, 2, 3, 4, and 5. And that's the same as the set B, which contains 3, 1, 4, 2, and 5. So really, we didn't need to introduce a new name for the same set, and we could have just said that this is equal to A. Okay, here's another example of a set, X, and it's equal to a set of ordered pairs or points in the XY plane, the coordinates, or we can interpret them as coordinates, and that contains the 0, 0, 1, 1, and 2, 2. Okay, so notice here with this set, X, that the order in which those elements appear does not matter because it's a set, but these kind of objects here, which are ordered pairs, okay, order certainly matters for them. So for example, the coordinate 1, 2 is not the same thing as the coordinate 2, 1. Okay, so these points would have different locations in the XY plane. So that's an example of a mathematical context in which order is important. And sets are an example of mathematical context in which order is not important, at least not for the sets that we will be looking at, okay? All right, so set membership. So this symbol here is the Greek letter epsilon, and that means belongs to, or is an element of, or is a member of. Those things are all equivalent, but usually we just say is in. So for example, okay, 2 is in A, because if we look at this set here, A, well, you'll notice that 2 is inside that set. 2 is in that set. It's a member of that set, or an element of that set. Okay, we could have written this over here, right? But what would be the point of giving sets names if you were just going to write them out in full all the time? Okay, so we usually won't write this here, and we'll stick to, we usually stick to this. Mathematicians are lazy, so whenever they can make their notation more compact, they will do it. Anyways, this here, this symbol is just like the negation of membership, right? So this means does not belong to or is not an element of, but we usually just say is not in, okay? So for example, 6 is not in A, because if we look at our set A up here, you'll notice that there's no 6 inside it, right? Okay, so it can get tedious to write all elements in a set, so often you can make your notation shorter and take advantage of the fact that elements of a set often have common properties, right? And you can almost always find a common property between all of the elements of a set, okay, depending on how creative or imaginative you want to be. So in this case, you would use this symbol here, and this means such that, okay? But just a word of caution, it only has this meaning in the context of sets, okay? So if you should really only write this symbol intending it to have the meaning such that if you are writing it inside set brackets, okay, the curly brackets, okay, because this symbol has other meanings in other contexts. So use it properly. So here's an example. Okay, so the set of elements of A that are less than 3 or strictly less than 3 can be written like this here. So this reads the set of all X in A such that X is less than 3, right? And if you recall that A was a set that contains 1, 2, 3, 4, and 5, well, look at that set and pull out all of the elements that are strictly less than 3. So that would be 1 and 2. Okay, so this set here is equal to the set that contains 1 and 2, right? Okay, moving on. So the set X that we mentioned earlier, that was the set of ordered pairs or coordinate points in the XY plane. It contained the coordinates 0, 0, 1, 1, and 2, 2. So it could be written like this. So this is just appealing to, or referring to a common property in order to write the set another way. In this case, it's not really less writing, but this reads the set of all ordered pairs or points x, y, such that x is equal to y, and 0 is less than or equal to x, and y is less than or equal to 2. Okay, but this is not the only way we could have written it. So for example, we could have written it like this. We could have said x, so I'll use a different pen. Okay, so x is equal to the set of all ordered pairs x, y, such that x is equal to y, and 0 is less than or equal to x, which is less than or equal to 2. Okay, so 0 is between, x is between 0 and 2 inclusive, and always remember to close the set. So if you notice here, we said x is equal to y, so really we wouldn't need to make reference to y over here, because if they are equal, then everything that we want to say about y, we could say by talking about x, and vice versa. Okay, so this here, that's not the only way I could have written that set. There are other ways, but that's just an example of how sets can be written in different ways by using the such that symbol and appealing to a common property between all of the members of a set. Okay, so subset, union, intersection, and the empty set. So this symbol here, the symbol means is a subset of. Okay, so for example, 2, 3 is a subset of A, and the set that contains the origin or the coordinate 0, 0 is a subset of x. This is x up here. Okay, and just maybe a few comments on the subset relation. Okay, so recall that this was our set A, and it equaled 1, 2, 3, 4, 5. So it contained these elements, right? And this set, let's call it S equals the set 2 and 3. Okay, so S is a subset of A. That looks a bit like a less than or equal to sign, so I'll just make it a bit more curved. Okay, so S is a subset of A, and what this is really saying is that every element in S is also in A. Okay, and this line underneath that that curly symbol that looks a bit like a C, this means that S could actually just be equal to A. Alright, because if you imagined that, let's take another set, so let's call this one S star, okay, and this equals 1, 2, 3, 4, 5, okay, well, is every element that's in S star also in A? Well, yes, it is. So we could say that S star is a subset of A. It satisfies this subset relation. Okay, so this line underneath is like leaving open the possibility that this set on the left-hand side just is the set on the right-hand side. But contrast this with our other set S, which just contains 2 and 3. Okay, we would just as, we would also be justified in just writing this. S is a subset of A without the line underneath. And leaving out that line underneath just means S is a subset of A, but S is not equal to A. Okay, so in that case, we would say S is a proper subset of A. Okay, so in this case, every element that is in S is also in A, but there are some elements in A that don't appear in S. So the situation would be like this. Okay, so this would be S, and there'd be some element outside here in A, which is not in S. Okay. All right. Anything else? Nope, I think that's it for now. So If we return to where we were, so okay, so the set that contains 2 and 3 is a subset of A, and even though this set doesn't contain all of the elements of A, it's still fine to use this symbol here instead of saying this. Okay. Oh, sorry. The sub is a proper subset of A. So both would be correct in this case. So it's a bit like saying if we say x is less than or equal to 3, we're still leaving open the possibility that x is equal to 3. And, you know, it's not incorrect to say this. X is less than or equal to 3, okay? Because for the statement to be true, okay, because it's an or statement, so only one of the conditions have to be satisfied. You know, x either has to be less than 3 or x has to be equal to 3 for that statement to be true. And in the case that x equals 3, we've satisfied one of those conditions, okay? So when x is not equal to 3, but it's something less than 3, so it's still true to say 2 is less than or equal to 3. Okay, so that's kind of like what's going on here. Okay, this is correct. Okay, and this is correct. Both are fine. Okay, so here's an example of something not being a subset, and we write the subset symbol and put a line through it. We strike through it when some set is not a subset of another set. So for example, the set that contains 2 and 6 is not a subset of A. Okay, because to be a subset, every element in this set has to be contained in A, right? And you'll notice that 2 is in A, but 6 is not in A. Okay, so only one of these elements satisfy what we need for it to be a subset. This element 6 does not feature in A at all. So this set that contains both of them, 2 and 6, is not a subset of A. Okay, so moving on, the union of two sets, A and B, is the set of all elements that occur either in A or in B or both. Okay, and is indicated by this symbol. It looks like a big U. So that symbol is the union symbol. So for example, if A is equal to the same set as before, and B equals 3, 6, and 7, then and we've got this set here, C is equal to -1 and -2. We'll use that in some example later. Okay, so then A union B is this set here. Okay, so really this is saying, look at all of the elements in A and put them in a set. Okay, so once we've done that, okay, so here's A in red and B in green. Look at all of the elements in A and put them in a set, okay? 1, 2, 3, 4, and 5, okay? Now look at all of the elements in B and put them in the set that you're constructing. Okay, so our first element is 3, and if we look at our set, we've already got a 3 here. And remember I said elements in a set are only listed once. Okay, so we're not going to write 3 again. Okay, we're not going to write our friend's email address a second time and send him 2 invitations. Okay, and then we look at 6 and we realize it's not in our set yet, so we need to add that one as well. Okay, so we'll put in 6 and then 7. Okay, so we've already got that, we've added that, and now we add 7. Okay, and we added all of these elements and we constructed the set A union B. Cool. Okay, so the intersection of two sets A and B is the set of all elements that occur in both A and B. So we indicate set intersection by this symbol here. Okay, so it's like an upside down U. And if we look back at A and B, what those sets were, well, okay, set intersection is well, exactly like asking what elements do two sets have in common. So it's asking what elements do the set A and B have in common, and if you look at both of the sets, you'll see that they only have two elements in common. So that's sorry, they only have one element in common, so that's 3. Okay, so that situation is like this. Okay, so we've got, this is A, and this is B. Okay, this here would be the set intersection. Okay, and the only thing that's inside here is 3 in the example we were just considering. Okay. Alright, and sometimes sets don't have any elements in common. Okay, so for example, we've got this set C up here that contains -1 and -2, right? And here's A. They don't have any elements in common because, I mean, you can see that immediately by observing that all of the elements of A are positive numbers and all of the elements of C are negative numbers. So they can't have any elements in common. So, you know, it might seem natural to say, well, if they don't have any elements in common, then the intersection of those two sets just wouldn't exist. There wouldn't be a set, but there is in fact a set, and we call that the empty set. And this is how that's sometimes written, and that makes sense because it's just a set with nothing written inside it, okay? But it's actually more commonly written this way. So it's like a 0 with a line through it, or the ancient Greek letter phi. So in handwriting, it's often like this, or you might see it, the line on a bit of a diagonal. Okay, so that denotes the empty set. And this is a common mistake. The empty set like this. This is the empty set. Okay, this is the set that contains the empty set, right? So let's make a bit. This is actually an element that's empty. So the idea of an empty set might be a bit counterintuitive, but you can think of it as like, you know, files. So when you are organizing your files, you might make folders on your computer, and a folder can be empty. Okay, a folder can contain no files, just like a set can contain no elements. You can have an empty folder just like you can have an empty set, right? But what if you had a folder and you put another folder inside of that folder, and that folder happened to be empty? Well, that would be like the scenario you have here. You have an empty folder inside a folder, and the outer folder wouldn't be empty because it contains a folder, right? But the inner folder is empty. So this is why this is not the empty set, because it's actually just not empty. Okay, so I think that's a good place to leave it. That's just some introductory set notation. It might seem like a bit convoluted to read, but it provides us with some mathematical machinery for speaking very precisely about mathematical entities and, you know, collections of objects and things like that. Okay, so the next video is going to be on real numbers and interval notation. If you enjoyed this video, hit the like button, subscribe, and perhaps share it with some of your friends. Bye for now.